Hi everyone. In this video I'm going to provide a walkthrough of multi-level regression in R using the lme4 package, and the example that we will be using is based on a presentation by Hawks in his 2010 text, Multi-Level Analysis Techniques and Applications. So in chapter 2 of that text he gives a demonstration involving student level data. So basically we have students who are nested within classrooms. Now before we get started here, let me note that you can obtain a copy of the data that I will be using at this link right here. I will make this available underneath the video description. The data will appear as an RData file, and it will be saved within a data frame that is called Hawks 2010 CH2. Additionally, I will include a link underneath the video description to this text file that you see open, and it contains the commands that I'm going to be going over. What I'll be doing throughout this presentation is essentially talking about the commands from this text file, and then I'll copy and paste it into R in order to expedite the presentation and to minimize errors. So let's go ahead and get started by just looking at the example. So this is from chapter 2 of that 2010 book, and the example essentially has student level data, again nested within classrooms. So we have students. The level 1 outcome variable is a measure of student popularity, and it's just a self-rating scale from 0 to 10, from very unpopular to very popular. The level 1 predictor variables will include pupil gender, which is coded 0 for boy, 1 for girl, and also pupil extraversion, which is another self-rating scale. The level 2 predictor will include teacher experience. So this is operationalized in years that range from 2 to 25. So let's go ahead and open up R right here, and we're going to use our structure function in order to take a look at our data frame. So the data frame, the data is already active in memory. I'm just going to type in str, and inside parenthesis I'll type in Hawks 2010 CH2 in parenthesis. So this is our data frame. This is a level 1 identifier variable, or student identifier, which we're not going to be needing in this demonstration. We have L2 ID, that's the level 2 identifier. So remember that the students are nested within classrooms, so this is basically identifying the different classrooms that each student is a part of. We have a level 1 predictor variable, extraversion, level 1 predictor variable, sex, which again was coded essentially 0 for male, 1 for female. A popularity variable is our level 1 outcome variable, and then the level 2 predictor is that teacher experience variable. Now before we get started trying to analyze our data, we're going to need to use the LME package, or basically call it up. So what we're going to use is the library function, and then inside parenthesis I'll type in lme4 and in parenthesis and enter. So just keep in mind though, to use the functions associated with this package, you need to have this package installed and then use the library function to call it up. So if you don't already have the package installed, you're going to need to do so before you start trying to use the library function to call it back up. So as you can see, that's not a problem here because I already had the package installed. Okay, so starting with our examples then, on page 17 of Hawks's text, you'll notice that you have a table 2.1, and there are two models that are presented. You have an intercept only model, that's model 0. That's essentially a baseline or null model with no predictors, and then you've got a model 1 with predictors included. So we'll start off with this one right here, and we're just going to generate the coefficients for this particular model. And just keep in mind that a standard approach in multi-level regression modeling is to test an intercept only model, and really that helps us to address the question of whether we have evidence of substantial clustering in our data. If there is substantial evidence of clustering, then that would justify the use of a multi-level regression modeling approach. If there's no evidence of any kind of clustering or dependence with respect to our observations, then perhaps a single level approach would make more sense. So looking at our syntax from our text file, you'll notice that this first line right here, basically what I'm doing is I'm generating the multi-level regression results and then saving it to a fit object that's being called M0. So what you'll notice to the right of the arrow, which is just a less than sign and then a hyphen, I have lme4. So that's the function to run our multi-level regression model, and that function is uniquely associated with the lme4 package. So for this to work, you've got to have that package already active in memory. Inside parentheses, you'll notice that I've got the name of the dependent variable, then a tilde sign, and then the remaining part of the model in terms of predictors and so forth laid out to the right. So the general layout of our model using the lme4 function is very similar to what you may be used to using the lm function in R. So you'll notice that the 1 is referring basically to the intercept for the model, and then there are no predictors that are included. And as I said before, this is essentially a baseline model, and all we're going to be doing is allowing the intercepts to randomly vary. And the intercepts within this model will be the classroom means for popularity. And what we're going to fundamentally do is test whether there's significant variation in those classroom means. So inside the parenthesis, you'll notice we've got 1, then a vertical sign, and then L2 ID. So this right here is what is allowing or specifying the model with the intercepts as randomly varying. We have following a comma, then data argument set equal to the name of our data frame, then comma, then REML is set equal to false. So the example that Hawks gives in chapter 2 uses maximum likelihood estimation. So in this case, we're going to set REML equal to false. If we wanted restricted maximum likelihood, we would say REML is equal to true. On this next line right here, you can see we're using the summary function, and inside the parenthesis, the name of our object, M0. So let's go ahead and just copy this and paste it into R and run it. And so now you can see we have our model fit information. You can see up here we've got the AIC, BIC, there's the log likelihood, deviant statistic, degrees of freedom residual. You'll notice that we have random effects that are given right here. This is the name of our level 2 identifier variable. You'll notice the name of our variance component, which is intercept. Then you've got the variance of the intercepts and then the standard deviation of the intercepts. The level 1 residuals, we have the variance of the residuals and standard deviation of the residuals. Down here we've got our fixed effects, and the only fixed effect in the model is the intercept. And this will be interpreted as the grand mean of the classroom means for the popularity variable. You'll notice that you do have a standard error given and a t-value given. Now if you want a little bit more information, you want to clean all of this information up, have it in tables, and also get a p-value associated with the test of the intercept or any other fixed effects, then another package that you can use is the JTools package. So I already have this installed, and so I'm going to use a library function to call it up. So we'll just type in library, then JTools in parentheses, and hit enter, and so now it's called up. So one of a function that's associated with this is the sum function, and you'll notice that there are 2 m's there, and inside parentheses I'm going to type in m0, which is the name of our fit object that we generated before. And so now you can see all of our information. So you'll notice there's the model fit information, the AIC and BIC. Here we have Nakagawa's pseudo R-square values related to the fixed effects, as well as the pseudo R-square total. You'll notice that our table of fixed effects right here, you have our estimates, standard errors, and so forth. There's our p-value. Most of the time you're not going to be interested in testing the statistical significance of the intercept. The test would actually be a test of whether we can infer that the intercept is significantly different from 0. So oftentimes that's not going to be of particular interest, but having this table is relevant, particularly later on when we start to look at the tests of the regression coefficients. When we scroll down, you can see that we have our table of random effects that are given, and you can see there's the standard deviations with respect to the intercepts and also the level 1 residuals. You'll see down here that we have the intraclass correlation coefficient, the value of 0.36, which is indicating basically that there is a pretty substantial evidence of clustering going on in our data. As such, that would support the use of multi-level regression moving forward. Now, if it's the case that we wanted to test the variance of the intercepts, we can actually use the ANOVA function right here, but that is a function that's associated with the lme4 test package, and notice that T is in caps. So just to show you, what I'll do is just copy this and paste it into R as well, and hit enter, and so you can see that we have essentially this is our term reflecting variance of the intercepts. You can see right here we have LRT, that's basically a chi-square value, the degrees of freedom, and then also a significance level. And so you can see this is indicating that we have significant variation in the intercepts, which would once again provide support for a multi-level approach moving forward. And just keep in mind also that when I refer to intercepts, I'm also basically we're referring to means. So in this context, they will be classroom means. Now, given that there are no predictors at level 1, then these would just be the unconditional classroom means. But if we had predictors incorporated into the model, then the intercepts are essentially the classroom means, but conditional on those predictors being included. Okay, so for model 1 that was shown in that table, what we're going to do is add in the predictors sex and extraversion as level 1 predictors. We'll add in teacher experience at level 2 as a predictor. The slopes for the level 1 predictors will be modeled as randomly varying and correlated basically amongst themselves and also with the intercepts. And I will say really quickly that the model will fail to converge, so that's what's going to happen. So you'll notice that I'm creating a new fit object called M1. There's our lme4 function, and then popular ~1, and then plus, then we have sex plus the extraversion variable plus teacher experience plus, and then inside parentheses you'll notice that I've got a 1 plus sex plus extraversion, and then vertical line, and then L2 ID. So laying out this specification, again, it's going to allow the slopes to randomly vary in addition to the intercepts, and also allowing the slopes and intercepts to correlate. You'll notice again we have got our data argument set equal to Hawks 2010 chapter 2, and then REML set equal to false, and we'll also use that summary function again. Just take a quick look at the output, and then we'll use the JTools package in order to get this information right here. So let's go ahead and just we'll start off with this one. I'm just going to copy and paste it in so we can take a look at our output. You'll notice that again there's our AIC, BIC, all of the general model fit information. Scrolling down, you can see under random effects we've got our variance estimates, standard errors, basically variance and standard deviations related to the intercepts. This is the variance and standard deviation for the slopes for sex, and then variance and standard deviations for the slopes for extraversion. And then you can see over here we've got the correlations for all of our random coefficients that are given right there. The level 1 variance and standard deviations are given right here. Under fixed effects, you can see there's our intercept as I mentioned before. We have sex, the coefficient, standard errors, t-values, and then now you can see we have p-values that are given, but all of this is kind of given in scientific notation. So using that JTools package can be a little more helpful in terms of kind of cleaning things up. Down here you can see it says model failed to converge. So that's what I was telling you about before. So I'll show you really quickly using the sum function what this would look like. This is based off the JTools package, and then what we're going to do is simplify our model so that it does converge. So in this case I'll type in sum and inside parentheses M1 and in parentheses, and there you go. So now you can see it looks a lot cleaner than what we had before. But do note that as you're looking through this, there's no statement about the model not converging. So it is a good idea to use that summary function first. If for nothing else, then if there is a problem with the model converging, you can get that message. Otherwise, you may just be interpreting everything else as if things worked out fine. Really quickly, I'll just use that ANOVA function just to kind of show you that in action again for M1. And there you go. So there's basically two likelihood ratio tests that are given in order to test the variance components. Okay, so we're going to do a Model 1A. So there's actually in Hox's chapter on page 21, you've got Model 1A, basically our main effects right there, and then you've got Model 2 with an interaction. So for this particular model right here, he basically removes sex as randomly varying. Nevertheless, it will remain in the model as a fixed effect. So here I'm creating a new object that's called M1A, and you'll notice that I've got, again, there's popular tilde 1 plus sex plus extraversion plus teacher experience plus, and inside parentheses now I've got 1 plus extraversion. And so in this case the intercepts are allowed to randomly vary, as well as the slopes for extraversion. And because both of these are contained in the parentheses as they are, they're going to be allowed to correlate. You'll notice again there's our vertical line L2 ID, and all the remaining code is exactly the same. So let's go ahead and run this. I'll go ahead and generate the summary of the model using that summary function, and we'll paste this in and hit enter. And so now there's no problem with model convergence. So as you can see right here, you can again, there's our intercept, which is just basically the grand mean of the conditional classroom means, basically conditional on the presence of our predictors included. There's sex right there, extraversion, and then our teacher experience variable that's given right there. And let's go ahead and just use that sum function from the JTools package. I'm going to just type in SUMM again, and in this case I'll type in M1A. And also if you want more digits, or you want to increase or decrease the number of digits, you can type in digits equals, and for this one I'll just type in 4 and hit enter, and so now you've got rounded off to 4 decimal places. So basically as you're looking at this, you can see that sex, remember the coding on that was 0 for male, 1 for female. So basically females were predicted to be more popular than males. Extraversion, there's a positive coefficient indicating that students who were more extroverted were predicted to be more popular. And then you've got this teacher experience variable right here. It's positive, indicating that students are predicted to be more popular in classrooms where the teacher has more experience, and all three of those predictors were statistically significant in our model. And then again, there's our ICC, and you can see our table containing the random effects and so forth. Now for our next model, we are going to include a cross-level interaction between teacher experience and extraversion. So here basically we have M2, and we are going to obtain the coefficients from the M2 column in Hox's chapter in table 2.3. And there are actually a couple of ways that we could lay this out. This first approach right here, you'll see I've got popular tilde, then 1 plus sex plus extraversion plus teacher experience plus extraversion star teacher experience. So this right here is capturing the cross-level interaction between teacher experience and student extraversion. And basically everything else is laid out in exactly the same way as what we've covered before. So we could either specify our model in this way, or we could use a little bit of shorthand. Down here is the same model, but you'll notice that we've got popular tilde 1 plus sex plus the extraversion star times teacher experience. And so you'll notice that we're not having to specify the individual effects of extraversion and teacher experience and then the interaction term as we did up here, but instead, since these two variables are part of the interaction right there, both the effects of extraversion and teacher experience and their interaction will appear in our output. So let's go ahead and run this model and generate our output. So I'm going to copy this and paste it in and hit enter, and so now you can see, looking at our output, that we have the interaction effect that's given. You can see that we have that interaction effect is statistically significant right there. We'll also quickly use the sum function associated with our JTools package. So I'll just type in sum m2 inside parenthesis, and there you go. So there's again our interaction. You can see it's statistically significant. So if I was positing that the relationship between extraversion and popularity is moderated by levels of teacher experience, then this would provide evidence of that moderated effect. Now, looking at our regression coefficients, just kind of unpacking things a little bit more, you can see again sex, we have a positive and significant relationship between that variable and popularity, essentially indicating that females were predicted to score higher on popularity than males. Extraversion, there's a positive predictive relationship that's significant. Just keep in mind that the interpretation of this coefficient is the predicted relationship between extraversion and popularity, essentially in classrooms with teachers who have no years experience. And so the slope for the interaction term is essentially reflecting the predicted change in terms of the relationship between extraversion and popularity with each year increase in terms of teacher experience. Okay, so since the interaction term is statistically significant, indicating that we have evidence of significant moderated effect of extraversion on popularity, we can also probe the interaction using a couple of functions from the reghelper package. So what I'm going to do is use the library function to call this package up, and then use two functions within it. There's simple_slopes, and then there's also graph_model. So let's go ahead and do this. So I'm going to type in library reghelper, and so now it's activated and ready to go. So next I'm going to type in simple_slopes, and then inside parentheses I'm going to type in M2 for that model. So now it's going to generate the simple slopes depicting the relationship between one of our predictors and the outcome variable at different levels of the second variable. And in particular, since I'm treating teacher experience as my moderator variable, you'll see right here I've got these numbers right here. That would be at 1 standard deviation below the mean on teacher experience. That would be the mean on teacher experience, and 1 standard deviation above on teacher experience. So the regression slopes, the simple slopes for extraversion at those three levels are these values right here. And you can see that all three of them would be statistically significant. But also notice that with respect to the values in terms of the slopes, you can see the strongest relationship between extraversion and popularity is at the lower value, at 1 standard deviation below the mean with respect to teacher experience, and you can see the values decrease with increasing levels in terms of teacher experience. So let's plot out those slopes. So we're going to use the graph_model function. Inside the parenthesis we're going to type in M2, which is the name of our model containing the interaction. Then we are going to type in the name of our variable that's going to appear on the y-axis, which is popular. Along the x-axis we're going to type in extraversion right here. And then lines, this is basically reflecting the different levels of the moderator. Our continuous moderator is teacher experience, so it's going to basically plot out these regression slopes that we just talked about at 1 standard deviation below the mean on teacher experience, at the mean on that variable, and then at 1 standard deviation above the mean. So let's go ahead and copy this and paste it in and hit enter. And there you go. And in fact, I should have mentioned, the default right here was actually at 1 standard deviation below the mean and at 1 standard deviation above the mean on teacher experience. But you can see that those slopes are quite dissimilar between them. So if there was no interaction, we would expect those lines to look a lot more parallel than what we have right here. So the lines are clearly not parallel, which is consistent with the idea that there is an interaction effect going on. Okay, what I thought I would do also is show you one additional model. It doesn't actually appear in Hox's text, but I did want to show you a situation that would include a model where we have two interactions going on. And I also wanted to show you how to essentially set the covariance between the random intercepts and slopes to 0, or basically to fix that relationship to 0. So right here I'm creating a new object called M3. There's our lme4 function, popular tilde, then I've got 1 plus. You'll notice I've got sex asterisk extraversion, so that's sex by extraversion interaction, plus the teacher experience plus extraversion by teacher experience right there. Now, one thing to note in terms of the interactions, if you want to generate simple slopes using that reg helper package that I was mentioning, if you have a situation where you have two interaction terms that are included in the model, it's going to generate the simple slopes for the first interaction term. So if you wanted to generate a ladder interaction like right here, then I would want to move this to the front and move the second one to the back. In this case right here, you'll notice that I've got just sex by extraversion. That's essentially an interaction between the level 1 predictors, and then we have our cross-level interaction that's given right here. Now you'll also notice I've got plus and then 1 vertical line there, and then L2ID, and then plus. You'll notice I have a 0 plus extraversion. There's our L2ID variable here, and so by incorporating that 0 right there in this part of our model, it's essentially specifying that our interactions, that our random intercepts and slopes will not be correlated with each other. So let's go ahead and just copy this and paste it in and run our analysis. And you will notice one thing. You get an error message down here. It says boundary singular fit. It says and then there's a question mark, is singular. So basically this creates a little bit of a problem in terms of interpreting our results. They may not be particularly trustworthy. If you want to read up more about this, we can just copy this and paste it in right here and hit enter, and you'll notice that information comes up on this particular issue. Okay, but at any rate, just for the purposes of completeness, you can see right here we have simple underscore slopes M3, and I went ahead and generated it right here. I just typed in simple underscore slopes M3 for that third model. You'll see again we have those error messages that are given, but we do have our simple slopes tests that are basically provided in this area right here, and then you'll notice that underneath we've got graph underscore model M3. There's our y variable is popular, the popularity variable, extraversion for the x variable, and then lines we're going to look at it by sex. So let's just copy this and we'll paste this in and hit enter, and here you see our results. So you can see the two regression lines by sex. So right, that's given right here. One other thing, just keep in mind that because this variable was not treated as a factor variable in the data set, it's giving levels by sex in terms of 1 standard deviation below the mean and then above the mean. It's not going to be particularly problematic in terms of interpretation, but I just wanted to kind of point that out. Basically, if you wanted values of 0 and 1, then the sex variable would need to be converted to a factor variable, and then when you run the analysis and then graph the slopes, then it would appear with values of 0 and 1 instead of the -1 standard deviation and +1 standard deviation. But that pretty well concludes this video demonstration, and I appreciate you watching.